Now the author suggests a method to solve problem when the force is a function of time. Right? So the Professor Merriam introduced the concept of impulse momentum diagram. So you cannot find this impulse momentum diagram from Hibbeler. I don't think people are using this approach to visualize the impulse momentum equation. Right? So if you look at this model of approach that Professor Merriam recommended, is that when we have a problem, after we identify that this problem has a situation when the force is a function of time, right? We need to isolate the particles and then represent the diagram of that particle with the vector notations of the linear momentum to represent the initial momentum, and then plus all the forces acting on the particles, right? We present with the impulse integrals, and then we have that will be equal to the final linear momentums. So we have a solid line represent the final linear momentum, and then we have a dash arrow there represent the initial momentum uh, with the total of linear impulse, right? So when we look at this diagram, it represents a kind of vector analysis. So the tip that Professor Merriam gave us here is that all forces exert impulse, right? All forces exert impulse. Any forces. So we have to remember that whether they do work or not, right? So all of them exert impulse. There are so many forces that may act to the body while they are in motion, and we need to simplify the problem by making engineering assumption that certain forces can be neglected for certain reasons. So Professor Merriam here suggested a two concept called impulse forces and non-impulse forces. Right, from the text, we are considering two situations. First one, force that is constant. When these forces acting on particle, and the other one when force is not constant, it varies during force is applied to the particles. So forces that are constant over time that is applied to the particle can be divided into three, right? The first one will be the impulsive force. The impulsive force is any forces that is so large but uh, being applied to the particle for a very short durations. I place a red line there to show an examples. For example, the forces, the impulsive forces, such as force exerted on the ball by the bat, right? So we have two particles here, the ball and the bat, right? So the force that exert by the bat to the ball is so large, right? So, but it's only appeared at a very short time. So that is an impulsive force and cannot be neglected, right? Because it's so large. And the other one is forces that magnitude is very small, right? It can be something that we assume that we have that force, but this is negligible, but we ignore them in order for us to solve the problem. And the third one will be the non-impulsive forces. Non-impulsive forces, it create forces, but when we compare with another forces, the magnitude is smaller, relatively so small compared to the forces that, for example, we have just now an example between the ball and the bat, right? So the ball has weight, and this weight is applied during the motion of the particles. But when compared with the force applied by the bat, it is so small that it can be neglected. We are looking now at the forces that varies with time, right? So normally the linear impulse, right, the integration or summation of forces, for this case take quite some time, right? And you mentioned here two ways that we can evaluate the linear impulse. The first one will be using the experimental measurement. So when we mention about experimental measurement, we are looking at the senses, right? So if you have experience using senses or using a data logger, for example, right, there is a resolutions of measurement, very accurate, fast response system of measurement can evaluate the measured value for very short time. But there are cases when we don't have that money to buy those expensive system. And for example, the bed, for example, if we don't have a system of measurement that um, can acquire data at very high frequency, we are not able to measure the variation of forces with time. And after we get the measurement, we are using the numerical integration in order for us to evaluate the linear impulse over a period of time. Well, now we look at the conservation of property here. We call as a conservation of linear momentum, and what does it mean, right? So we have equation just now, the linear impulse equations, and in this equation 328 is a specific case, right, for that linear impulse equation. So we can see that there is one term disappear from this equation, which is the linear impulse of that act on the body of particles. Yeah. So what it says here, the resultant force on the particle is zero, right? So we are talking about the net force. So the net force is zero, or all the forces acting on the body when we made summation of it over a period of time. So we find that value is zero, and we say that the linear momentum of the particle is conserved. We quantify that by calculating the linear momentum before and after the force being applied. So we can say that there is no changes in the linear momentum. Next, we look at the